Alright, so this is a screencast to make up for our lost snow day. This is basically we're going to tackle the question of what is energy. Other questions of interest that we'll answer throughout this unit is what is a horsepower, 100-watt light bulb, what does that mean? Do we have an energy crisis? And what's E equals mc squared about anyway? That famous equation by Einstein we'll spend some time looking at. So the question is, what is energy? And it's a hard question to answer because we can't hold energy in our hands. We can't see energy. It's kind of like, can you see the wind? No, we can't see the wind, but we can see what the wind is doing. If you see the leaves rustling, then you know that there is a wind there, even though you don't see the wind itself. So it's hard for us to discuss what energy is. The only thing that we can talk about is, what does energy do? But to tackle this question of energy, we have to look at this concept of work. Usually when you think of work, lots of different things come to mind: homework or physical labor or filing or whatever. We have a lot of different meanings for work, but in physics there's really only one definition for work. When we talk about work, work is really a transfer of energy, transferring the energy from one object to another. So our definition of work is a force times distance. So you apply a force to an object over a certain distance, you've done work on it. Our units, actually I shouldn't have said distance, I should say displacement. Because if I push an object around in a circle, my distance might be non-zero, but the displacement would be zero. And so technically I didn't do any work. Anyway, you have to change an object's location to do work on it. The units are going to be a Newton times a meter, but you may be more familiar with the joule from your days in chemistry. That is a measure of energy. The abbreviations for the joule, Newton, and meter are here. If we look at the fundamental units of the joule, it's a kilogram meter squared over second squared. Alright, so we'll do a quick example. I pull a cart 5 meters with 10 newtons of force. How much work did I do? 10 times 5 gives us 50 joules. Easy peasy, right? No problem. What if I lift a 2 kilogram mass, a total of 1.2 meters? How much work did I do on the mass? It's force times distance, which is equal to the force that I had to exert here is the force of gravity on the mass. So that becomes that the work is mass times acceleration due to gravity times the distance lifted, 2 kilograms times 9.8 times 1.2 gives us 23.5 joules, or using the appropriate number of sig figs, that would be 24 joules. What if I hold the mass stationary? So I'm still applying the force of gravity on the mass, 2 times 9.81. But if I'm not moving at a distance, then I'm doing 0 joules of work. So even though I'm putting in effort, I'm not actually technically doing any work. The signs of work. If force and distance are in the same direction, then it's positive. If I'm applying a force in the opposite, the direction of motion, then it's negative work. And it's 0 if the force is 90 degrees to the displacement. Also, work doesn't give us any information about the time or velocity. You don't know how fast you're going or how long it takes to get there. It's just a measure of the energy that you're putting into the object. Also, work can be done by friction. So let's say I slide a box across the floor. The box is going in one direction. The force of friction is in the opposite direction. So in that case, friction is doing negative work. Now, the slightly tougher question of what if the work is not in the exact same direction as the displacement? What if it's at an angle? For instance, let's say I'm pulling a cart at an angle and the cart is moving horizontally. Well, the equation changes slightly. Instead of work equaling force times distance, it's actually the cosine times the distance, where the angle is the angle between the direction of motion and the direction of the force. So it's essentially the x component of the force vector. So if we have work done in the x direction, this is the formula we would use If you're pulling up, but it's moving in the X direction, then you're not doing any work. So for instance, a waiter carrying a glass, he's applying a force upward on the glass, but the motion is horizontal. So he's not technically doing any work. He'd have to actually lift it up or down to start doing work. And if the force is in the exact same direction as motion, then cosine of 0 is 1, so it's just work is equal to force times distance. So this is how that formula applies to these different situations. So let's actually do a situation. Somebody's pulling a cart at a 45 degree or 34 degree angle. What is the work done on the cart? So I'm still applying VFW. Is there any work done in the Y direction? No, there isn't. What about the X direction? Well, the cart's moving in the X direction, and there is a component of force in the X direction. So we would use work is equal to F cos theta times the displacement, how far you've moved in the X direction, which is given in the problem. 104 joules. It's really not too hard. What is the work? What if we add friction to this situation? What is the work done by Michelle on the box? She's pulling horizontally this time. So 45 newtons. The angle is 0. She's pulling directly horizontal. So this is work is equal to force times distance. 45 newtons times 4 meters gives us 180 joules. What is the work done by friction? Remember, friction is equal to, the force of friction is equal to mu times the force normal times, and for the work, multiply that by the distance. So this is just a series of substitutions. This is the work, is force times distance. Force of friction is the force being applied this time in the opposite direction. And force of friction is just mu times force normal. And the normal force in this case is very simply mg, force of gravity, because none of the forces are pushing up or down. Just the force of gravity pulling straight down, so the normal force has to be equal to the force of gravity. If you plug in all the numbers, you get negative 113 joules. Remember, the displacement in this case is to the right, but the force is to the left. So what is the total work done on the box? It's just the difference between the work done by Michelle and the work done by the force of friction. And that's it. That's all there is to work, or at least what you'll have to know for the upcoming test and midterm. We'll see you on Monday.